Okay, I think we're officially recording. All right. So, what we're going to talk about today, it's starting a new chapter. And so, just to remind everybody, uh, next week's midterm exam is not going to have any of the stuff we're going to talk about starting today. So, it's just really going to be chapters 3 and 4. Okay, so none of this uh, is going to be on the exam. Um, I guess I'll have to figure out the exam as well, how to deal with that. Um, have any of you had the experience of taking like an online exam via like a lockdown browser or something?
No.
Okay, so yeah, I guess we'll work through it together, and hopefully it'll be really seamless. It'll probably be, you can access it for, doesn't have to be exactly at this time frame. And so I think once you open it, then you'll have, an hour. I'll give you like an hour and a half or something to do the exam. But I'll talk more about that as I figure more out myself. So hopefully that'll all work out smoothly. But anyway, so chapter 5. So this chapter is really, really key because we're going to start talking about electronic structure. So where do the electrons reside in the atomic structure? And so the first thing we have to talk about is the electromagnetic spectrum. So this is kind of probably a review from physics class that you had, this probably, or back to high school. And so electromagnetic radiation has an electric component and magnetic component, and so, hence the name. And so it's characterized by wavelength, frequency, and amplitude. You can just think of some place that I just traveled back from, and maybe you did as well. Florida, watching the waves come in uh, on the beach. And so, what these look like. So, a wavelength is really just the distance between two crests, or you could talk about between two troughs or valleys. Okay, so this distance here, hopefully you can see me move my mouse here. Um, so this distance here is a wavelength as well as that distance. Okay, and its symbol um, is that. Okay, frequency is nu, so lambda. Frequency is nu, and that is if you imagine that you have a fixed point, maybe we'll say this point here, where my mouse is, and if you imagine all of the wavefronts passing that fixed point per unit time, and so as a result, frequency has a unit of seconds to the minus one. Okay, and that's actually exactly the same as a hertz. Okay, so if you've heard of a hertz or your radio. So what's your favorite radio station? Somebody just shouts one out.
101.1 WRIF the riff.
101.1 is it? Okay. So that's in megahertz. Okay, and so that would be many hertz. Okay, so we'll look actually at some questions later where we have to convert between this unit. So remember, it goes kilo and then mega and then giga and tera above that. Okay, and so those all refer to the frequency of radiation. And then the third parameter is just the amplitude, and it's really not defined as this whole distance, but it's really just from this baseline to the top of the crest, or I guess you could say, to the bottom of a valley too, or trough. Okay, and so those are wavelength, frequency, amplitude, and we're going to talk more about kind of the relative position of these, later today. Wavelength very frequently is given in units of nanometers, as shown here. Okay, so we've got violet light is at the smaller nanometer ranges, and then IR radiation or radio waves, for instance, is at very long wavelengths, so higher wavelengths. Okay. Yeah, if you have some background noise, maybe if you mute your mic for a bit, please. Okay. So any questions so far? Easy stuff. Okay. Okay. Whoops. All right. So this is just a illustration showing the different regions of the EM spectrum, and so we're going to talk about, I guess, energy a bit later on today. And so the most energetic radiation is right here, so like gamma rays. So that would be something that if you were to be exposed to gamma rays, it would cause a lot of tissue damage, like instantaneous tissue damage. So very, very energetic. And then we move to X-rays that are pretty energetic as well. So if you go into the hospital for a diagnostic exam involving X-rays, you have to have the lead vest on and everything, so to protect. And so again, very energetic radiation. Then we get to less as we move this way. Okay, so as we are moving this direction, notice that frequency is getting less. Whoops, not the whole thing. Frequency is getting less, but wavelength is getting higher. Okay, so there is this relationship between frequency and wavelength that they are inversely proportional to one another. Okay, and this is just kind of showing, a wavelength of light in the radio waves. It's kind of the dimensions of us. It's in units of like individual meters. Versus a microwave is kind of like the distance of, or the length of a fingernail, and then a pinhead. And so virus, this nasty coronavirus, for instance, has dimensions that are similar to a UV wavelength. Okay, and then individual atoms have wavelengths that are in the X-ray range. And so this is why, if you want to know the structure of solids, you hit a solid with X-ray radiation. And so that is about the same wavelength of individual atoms, so then you get the fraction of those X-rays. And then it tells kind of where the atoms are in three-dimensional space.
Right.
Okay? All right. Oops. There we go. Okay, so your first equation, the equations in this chapter are going to be very simple, but they are something that you're going to have to memorize for future exams. I will give you the constants. So this is the speed of light in a vacuum. So 3 times 10 to the 8th meters per second. In air, it's a bit slower, but it still, approximates to about 3 times 10 to the 8th, but it's just a little bit slower. And so you can convert between wavelength and frequency using this equation. Okay, so showing it kind of on the whiteboard here. If I want to, let's say I want to solve for wavelength, then you can rearrange that C divided by frequency. Okay, or if you want frequency, it's going to be C divided by wavelength. Okay, so you can get either parameter if you're given one. Okay, you're just using the speed of light and then dividing it by whatever you're given. Okay, so the type of question that would apply to is this. Okay, so by the way, if you want to go back to a slide or if you have questions, feel free. I know we're not in the classroom, but feel free to stop me or whatever. So this is a light, blue light. It has a certain frequency. What's the wavelength? And so here you're just using the speed of light, and then you're doing a conversion into nanometers.
Why is that clock an hour off still?
Oh, pardon?
Okay. I was going to say it was confusing me this morning. I have to worry about the time change.
Oh, okay. um, yes. So yeah, if you're given this frequency, okay, so that goes on the denominator, okay, and then in this question, I guess they're converting the speed of light into nanometers, and then you get your answer directly in nanometers. I guess another way you could do the question would be to just very simply do just 3 times 10 to the 8th meters per second, and then we've got our 6.88 times 10 to the 14 seconds, okay? And then if you do that conversion, let's see, so 3e to the 8th divided by e to the 14. Okay, so you get 4.36 times 10 to the minus 7 meters. Okay, and then you can convert that to nanometers. Okay, so I guess either way, you could either decide to convert the speed of light into nanometers right away, okay, since they want that, as the answer. Or you could just, leave it as is, and then at the end, convert this. Okay, so the way to convert it again, just to remind you, because maybe it's been a little while since we did unit conversions, but you have meters, and then remember meters is here, nanometers is there, and so 1 meter is a whole bunch of nanometers, right? And so then that'll give you 436 nanometers. Okay. All right. So is everybody cool with kind of either strategy there? Yeah. Okay. All right. I'm not hearing anything, so I assume it's okay. All right. All right. So that is dealing with light, or the electromagnetic spectrum, as really having wave-like properties. But what we're going to see is that electromagnetic radiation also has particle-like properties. And some of the earliest discoveries of this was from experiments that Einstein was working on. And he developed a concept called the photoelectric effect. And so this, whoops, I just dropped my phone. What this implies, or what it describes, is if you have a clean metal surface and you just hit it with light, at a certain frequency, you won't have any electrons being ejected from the metal, but as soon as you reach some threshold value of energy, you have enough energy to kick off some electrons. And so you can think of it as, this is a piece of glass, and if you kind of just toss a baseball to the glass, it's just going to bounce off. But if you throw it, with a fair amount of energy, it has enough energy to break through. Okay, so we call that the threshold energy level. And so this is shown, his experiment really is shown here. Okay, so where you've got, the y-axis is how many electrons you're kicking off from your metal surface, and this is frequency. And so we're going to see an equation here in a second that frequency is directly proportional to energy. Okay, so energy is increasing this way. And so, at a certain energy, you are not, kicking off any electrons, but then as you reach a certain frequency or a certain energy, now you have enough energy to kick off electrons. Okay, and so so this indicates that there are particles that can be emitted from a surface. Okay, so it's really the first experimental evidence of particle-like properties for electromagnetic radiation. Okay, Oops. How do I move? There we go. Okay, so this is the equation. Something you will not have to memorize is the Planck's constant. Okay, so this value is h. Okay, and so therefore energy is directly proportional to frequency. There's another equation that is not on the PowerPoint, but it is this. So energy is equal to hc over lambda. Okay, and so in other words, energy is inversely proportional to wavelength. Okay, so in other words, if you have energy or wavelengths, let's say these wavelengths, so red, if we look at the visible spectrum, red is about 800 nanometers as far as its wavelength, and blue is, I don't know, like at the 400-ish range. Okay, so based on their wavelengths, which is going to have the highest energy value, red or blue?
Blue.
Yeah, blue. Yeah, right. Yeah, because it is inversely proportional, so the lowest number is going to have the highest energy. Okay. All right, so let's pull out your cell phones and do a few of these, the Chem 101s. Okay. This first one, EM1. It looks like a few other people did it already, but okay. Oops. Oh, don't view feedback. No. Okay, you didn't see that. Show question. There it is. Okay. Okay, so red light has a blank frequency and a blank wavelength than UV rays. And there's the spectrum for you.
Is it supposed to stop at it? It's trying to.
Is it working for everybody or no?
What is his name?
Give us like a second to pull it up.
Okay, cool. That's what people are thinking so far.
Yep. Yep. I had to stop at my grandma's on my way home from my hair appointment to pick up a cake for her. I think she made her a cake or something. I'm assuming they are. They're just not having open dine, like in dine. Because I've seen like things being turned into delivery. And otherwise, they're completely gonna not have service.
So it looks like most people are picking D, and that is the correct answer. So good job. Yeah, so it has a lower frequency and a longer wavelength. Okay. Now, as far as energy, what do you think? So red light would have a blank energy than UV.
Yeah. I didn't know he was going out there after vacation.
Anybody? So red light has lower or higher energy than
Lower.
UV. I heard lower. Anybody think higher energy?
I don't like how they do this because you can see everybody.
No? Okay. Yeah, so red light. Yeah, if I go back to the little thing here. Yeah, so red light, as far as energy, red light would have less than blue light. Yeah. Okay. All right, so let's go to the next one. AM2. Oh, this is really delayed here. Okay. Okay, so show the question. So this is asking, what is the frequency of green light that has a certain wavelength?
Did you have those Clorox wipes or did you have to go buy them?
Madison Wallace, can you please mute your thing? Thank you.
All right, so it looks pretty close with a few answers so far.
Hey, Professor, what is C again?
C, oh yeah. Yeah, let me put that up here.
So, like, I remember you saying that you had to multiply by something, and,
There, this
Good.
one.
remember what?
There you go.
Yeah, so that's just C, so it's just 531 about that.
Yeah, so, yeah, frequency, so it's going to be that. Yeah, so you're just substituting it in. And it was, what was the wavelength? 531? Nanometers. So, I guess I would probably do the conversion of the nanometers into meters, probably. And so here's a little trick. You can say, if you want this in terms of meters, you can say that 531 nanometers is the same thing as 531 times 10 to the minus 9 meters. Okay, it's not proper scientific notation, I know. But I see people, go the wrong way when they convert this sometimes. So in other words, on the exam, you might be tempted to say, oh, okay, it's that. So then that's 5.31 times 10 to the minus 11, putting it into proper scientific notation. So it's really, this is really the same as 5.31 times 10 to the minus 7 meters, okay? But if you leave it like that, your calculator will, figure it out for you. And then that way you don't make any kind of errors by 100 that way. Okay, so if you plug that in the calculator, let me see, 3 times 10 to the 8th, 31e to the 9 minus. So, oh great, and mine didn't put it in scientific notation. So 5.6 times 10 to the 8, 9, 10, 11, 12, 13, 14, I guess. Yep, so yeah, looks like the majority of you, yeah. And the units are in hertz or seconds to the minus 1, yeah. Okay. So any questions about that? Those who picked this or put in this answer, 10 to the minus 5? Okay. All right. Let's try another one. So energy 1. This one. What happens to the energy of a photon if the wavelength is doubled? Okay, and again, let me show you on the whiteboard here. So the equation here is really this. Okay. All right, yeah, so I see consensus on this one. Okay, so you are right, yeah. So if you're doubling the wavelength, okay, then your whole energy will go down by 1/2, yeah. Okay, cool. And that's an exact question. Actually, I pulled this from the midterm last semester. So again, it won't be the one next week, but I guess your third midterm, I pulled it off of that. So very typical question. Okay, and then the last one of today is energy 2. Okay, so the energy of a photon with a certain frequency, and they give you the weird formatting, but yeah, they give you the Planck's constant here. There we go. So the equation is that. And whoops, ran out of room here. 10 to the 14th. Okay, so this one is really simple because you literally just plug right in. Okay, and then you get your answers in joules. Okay, so let me just double check here. E to the minus 34. Yeah, so 4.64 times 10 to the minus 19 is correct. Yeah. Okay. Now, what would you do if the question, and this is one I saw in a final exam one time, the ACS final, they picked a radio frequency. So let's say, what was that radio station? I don't listen to FM, so I don't know. 101.1, did somebody say?
101.1 WRIF, the riff.
Yeah, okay. That's great. Yeah, you should work for the radio station. That's perfect.
I should.
Okay, so what do you do if you're given this frequency and you want to know its energy? Okay, so we set it up the same way. Minus 34 times frequency. Now, though, we have to get it in terms of just hertz. And so do you remember how to do the conversion between mega? So 101.1 megahertz. And then if we're going to do that conversion, so 1 megahertz is how many hertz, do you think?
Is it 100,000?
Yeah, 1 times 10 to the third would be kilohertz.
Kilo.
And then, yeah, another
1
one.
times 10 to the 6.
Yep.
6.
Yeah, exactly. Yeah. So, okay, so again, kind of your rough scientific notation. Okay, if you put it in like that. Okay, then it would be, what is it, 6.626 e to the 34 minus times 101.1 e to the 6th So I get 6.70 times 10 to the minus 26 joules. Okay. And so if you compare up here, okay, this was, I guess it was like green light or something. I think this is in the range of like the visible region of the spectrum, okay, where you've got 10 to the minus 19-ish joules. Now radio waves, now we're down to 10 to the minus 26. Okay, so it's a lot less energy as we move our way down toward the radio. Okay. All right. So any questions so far? Okay. All right, so there's a concept called quantization of energy, and it sounds like a lot, and actually it is. If you go on to take more advanced chemistry courses, you'll get into this in a lot more detail, and it's really gets into hardcore math, where you're doing integrals and all that fun calculus stuff that you learned. But what it really is saying is that we have discrete energy levels in an atom. And so, for instance, we're going to see this tomorrow when we look at, where do the electrons reside. But we can talk about an increase in energy. And instead of having a continuum of energies that electrons can kind of fall into, we have discrete levels. Okay, and these are called orbitals, okay, like S and P, different orbitals, different types. But that's what we mean when it's quantized, that you only have discrete energy levels instead of a continuum. Okay. And this was from early experiments by Niels Bohr, for instance. Here was the first person to really propose a model for an atom that you're probably familiar with, from high school, where you have, remember this deal, where you've got the nucleus that's positively charged, and you've got kind of these orbits around it. Okay, these are where the electrons are. And so that's the Bohr model for atomic structure. It's not really correct, okay, and we're going to talk about, what the orbitals actually look like. But it's actually a really good approximation for calculating how much energy does it take if you want to take, let's say, this electron and move it from this orbital to that one. You can actually do the calculation using this Bohr model, okay? Or if you have an electron that's way out here, how much energy does it release as it goes to this orbit? Okay, so you can do those calculations, and I'm going to show those, either on Tuesday or next week. We'll talk more about those calculations, but the Bohr model is actually quite useful for certain things, but it's not so realistic when we're talking about actual shapes of orbitals. Okay. And so this is just showing kind of that model. And what's important about this model is that if you have an electron here, let's say in this first orbit here, for you to move it from here to ones that are further away, it actually takes energy because, again, electrons are negatively charged and the nucleus is positively charged. So you've got that attractive force between an electron and a nucleus. And so for you to move it away, you have to offset that. So you have to hit it with energy. Versus when you have an electron falling from higher to lower, that is going to emit a certain amount of energy. Okay, so it's very frequently will emit light of a characteristic frequency. So you could get like X-rays out of it, or blue light, red light. It all depends on how far it's falling. Okay. Okay, so the equation that really talks about energy having light, both kind of wave properties and particle properties, is this equation. So it's called the de Broglie equation. It's another one that you're going to have to remember. So here, just to keep a tally of the ones you're going to have to remember, it's this one. Okay, and then from that you can, do the two derivations, like that, that, or that. Okay, and then there's this one and this one so far. Okay, and then I guess add this one to the mix. Okay, H over mv. Okay, and so this combines both particle-like properties, because remember, I guess in physics, where did you see m times v when you're describing what, really?
Density?
No. Yeah, so if you're talking about kinetic energy, right? So kinetic energy, remember, is 1/2 mv squared. Okay, so you got mass, velocity. Okay, and so that's really talking about, if I'm going to throw a baseball through a piece of glass or something, right? So that is, kind of a bulk object that will have a certain momentum, and a certain velocity. Okay, so that's kind of this denominator. Whereas over here, you've got Planck's constant and this lambda, which talks about it now in wavelength terms. Okay, so you've got this one equation that kind of describes both, and so you can actually calculate the de Broglie wavelength of a bulk object. So for instance, this. Okay, so what's the de Broglie wavelength of a small car? Okay, so something you can see with your naked eye, obviously. So it's like this large object. You've got a huge mass, okay, and then it's traveling at a certain velocity of so many meters per second. And so you just plug it in. Okay, so you plug it into the equation. This is a different way to illustrate Planck's constant. Okay, so a joule. Okay, so this is a different way of saying it's joule seconds, really, is this unit. Okay, so I guess you need it in this form to cancel out the kilograms. Okay, and so this would be given to you again on the exam, and I would give you these units too, so you don't have to kind of remember this. But you plug it in, and you see that you've got an insanely small de Broglie wavelength. So it's 10 to the minus 38 meters. So it's kind of saying that something bulk, like a baseball or a car, something like that you can hold in your hand or sit in, it's really not described as having wave-like properties. It's pretty well all particle-like. Okay. But if you were to do the de Broglie wavelength for a subatomic particle like an electron, now you start to have larger wavelengths that kind of make more sense. Okay, so what it's saying is that you have these very, very small particles like electrons, protons, that are better described as waves, but bulk objects like a pencil that I'm holding in my hand here is more like just a particle and not a wave. Okay. Okay. So I'm not going to show the math behind the orbitals, and so this is something that is going to be a lot of hand waving, and so Schrödinger was the first scientist to really come up with mathematical functions of what do individual orbitals look like. Okay, and so this is where, if you've heard of s orbitals, p orbitals, d orbitals, those different shapes that we're going to talk about tomorrow. This is all, they're all mathematical functions, and it really comes from Schrodinger. And the story is, I don't know if I believe this, but the story is that he was skiing in the Alps, and he was just so obsessed with coming up with a theory to explain shapes of orbitals, and just really finding out where do electrons reside in an atomic structure, that he couldn't think of anything else, but he decided to just go skiing, to kind of take his mind off it for just a bit. And he started down one of the ski slopes, and as he reached the bottom, he skied right to his chalet, and he thought of this theory as he was skiing down the slopes, and he went right to his chalet and wrote the theory. And so it sounds grandiose. I don't know if I believe it, but but yeah. So the story goes. It was then combined. Heisenberg took it to a little step farther, saying that if we know where an electron is, then we really don't know the path that it's following, and vice versa. And so we really can't know both the position or the pathway at the same time. Okay, so it's called the Heisenberg uncertainty principle. And so kind of the only thing we're going to really exploit from the Heisenberg uncertainty principle is that where we're talking about orbitals, like an s orbital for instance, it's just a probability function. So it's the likelihood of finding an electron in a certain region of space. We can't be 100% sure exactly where the electron is in that orbital, but we know kind of the region in space where it could reside. Okay. All right, so just to kind of set it up, and then we're going to finish this tomorrow. Schrodinger's theory, what it was really showing is he came up with a wave equation. So a mathematical function to describe an orbital. And so he solved that, and then he came with a wave function. And so then if you square this wave function, that gives you the probability. And this is really what we are all familiar with. So, if you're familiar with s orbitals, are spherical in shape. P orbitals are those little dumbbells, okay? And then you've got the d orbitals that are kind of weird, like you've got this little donut one, okay? And so you've got all these different mathematical functions for different types of orbitals, and they are really just probabilities of finding an electron in a region of space, okay? And so tomorrow we're going to talk about the quantum numbers that describe these wave functions or these orbitals, okay? And some of them, like n, will really be related to the size of the orbital. L will be related to the shape, and then m sub L will be how many there are. And so we're going to look at these quantum numbers and see how that translates to the different types of orbitals that you have. Okay, so I think we have reached our 50 minutes here, so I will end it there. And so again, thank you for joining me today, and yeah, stay healthy, stay safe, everybody. And I guess I will see you tomorrow. Virtually see you tomorrow. Okay.